So today we're going to take it one step further with our inequalities and talk about solving compound inequalities. So this kind of ties to an idea that we hear about in LA called a conjunction. Now, those three favorite cars in LA are and, but, and, or. But in math, they're going to be the and the or. And that's what's going to be coming into our inequalities. This picture actually almost tells the whole lesson. So when we have an and situation, which I'll explain in a second, our graph, our inequality is often going to look like what I call the dumbbell. It looks like a weight. And the or looks like two arrows going in opposite directions. So before I get ahead of myself, let's move on and just start talking about what does it mean to have a compound inequality. So back in the days when we could do these things, imagine having choices for the weekend that you could go to dinner and the football game. What does that mean to go to dinner and the football game? It means that you're going to do both. If you were going to go to dinner or the movies, remember those days? If you were going to go to dinner or the movies, in English, that would mean one or the other. In math, it means one or the other, or really both. So here's, let's bring it back to math. So here's an example of an inequality that is a compound inequality. The word compound just means more than one. So we want to know all the numbers that are less than 5 and greater than or equal to -3. Now, can you think of a number that is less than 5 and greater than or equal to -3? Maybe you thought 4, maybe you thought 0, maybe you thought -3. Maybe you thought 2.5. There's actually an infinite number of numbers that are less than 5 and greater than or equal to -3. So basically, we need a graph that's going to show all those numbers. And it's not the number -10, because -10 doesn't make this part of the inequality true. And it's not the number 8, because it doesn't make this part of the inequality true. So can you sort of see this graph sort of coming out of this situation? So here is the -3 with the closed point because it has the equals component. And here's the 5 with the open. And here are all the numbers. So -2, -1, 1/2, 2.7. All of these numbers would make both of these true. Now, can you think of a number that's greater than 6, or think of a number that's less than 1? So in this case, it just has to make one or the other true. So the graph will end up looking like this, where here is the graph of all numbers greater than 6, and here is the graph of all numbers less than 1, and it has to make one or the other true. And those are the pictures that I just mentioned on the conjunction junction, that an and tends to look like a dumbbell, like a weight, and an or will tend to look like two arrows pointing in opposite directions. And that's the majority of the time. Now, there are a couple of weird situations, so let's just talk about those. They don't happen much, but, can you think of a number that is less than or equal to 3, or a number that's greater than -2? And if we were going to graph those two pieces, it would look something like this. So here is the top graph is the greater than -2, and the bottom one is the less than or equal to 3. And we need to kind of put these together in one graph. You would never leave this as a graph, okay, because it's not put together. So what is true? So notice that all the numbers down here are part of this graph. The -2 is on this one. All of these numbers are on both. And then over here. So do you notice that really all numbers work? So if we were going to put these two graphs together, we would have the top graph would be the appropriate graph. And basically all numbers work. No matter what number you pick, it'll make one or the other or both true. So we wouldn't leave these graphs, just to let you know. We would, throw these out, which I don't have them grouped, so I won't do that. But this would be your graph. And that's just sort of a weirdo on an OR. You still can see that the two graphs are there pointing in opposite directions, but when they overlap, they turn into all real numbers, basically. Now, can you think of a number that is less than 4 and greater than or equal to 8? And you're sitting there kind of scratching your head, right? So here are the two pieces. Here is the numbers less than 4. Here's the numbers greater than or equal to 8. And notice there is no overlap. There is no part that makes both true. So really, this graph would be a no solution. There's no numbers. And you wouldn't leave this graph, you'd cross it off. So you would have an all real numbers for this one and a no solution for here because these don't overlap. Those are kind of the weirdos. Doesn't really happen much, but I just wanted to make you aware of those as we go forward. So a compound inequality is two inequalities, and they're combined either by the word and or the word or. The word and, there is also something else we can do with an and that will sort of imply the word. An or will always have the word or in it. Solutions to and compound inequalities must be solutions to both of the two individual inequalities, and solutions to or compound inequalities can be solutions to either the individual inequalities. So, just an example in the real world. We'll start with one and we'll end with a real world example. But today's temperature will be above 32 degrees Fahrenheit, but not over 50 degrees Fahrenheit. Let T represent the temperature, and two inequalities are right here. So here is it's greater than 32 degrees. Here is it's not over 50, which means it's less than or equal to. And the temperature is going to satisfy both. So that is an and. So what I'm going to tell you is an and can be written this way with the word and, or it can be done what I call a squeeze play. It can kind of say, well, the temperature is in between these two. So it has to be greater than 32 and less than or equal to 50. And in this one, the word and is implied. Again, a Woodruffism, as I call this kind of a squeeze play. It's the idea that the runner gets sort of stuck in between the two bases if you're thinking about softball or baseball. So the variable gets stuck in between the two endpoints. And it creates this graph, which again, another Woodruffism is that it looks like a dumbbell. Okay, so let's start doing some solving here. So solve and graph the solution. 2 is less than or equal to x plus 5 and less than 9. So basically what you've got is the x plus 5 is greater than or equal to 2, and the x plus 5 is less than 9. So you can write it as what I call the squeeze play, or you can write it as two separate inequalities. So when it's two separate inequalities, this was our last section. You just solve each one. So now this one, you would subtract, we're trying to solve for x, you subtract 5. That's not the glitch. You don't switch the inequality. So you've got x is greater than or equal to negative 3. And over here, we would subtract 5, and you get x is less than 4. Now, your final answer must include your conjunction, your and or your or, okay? So you could write it this way, or you could squeeze it kind of back together. And in this case, the and is implied. But one of these two would be your final answer. Now, if you're going to graph it and you have the two pieces, basically the x is greater than or equal to negative 3 is the top, and the x is less than 4 is the bottom. And you're looking for the parts of the graph that make both true. You would not leave this as your graph. You would realize that none of these points that are less than negative 3 are part of the and graph, and none of these points that are greater than 4 are part of the and graph. So you'd end up with what, again, I call the dumbbell. So this would be your graph. It's really easy to graph the squeeze play. You put the negative 3 here, you put the 4 there, you fill this point in, everybody in between. So with an and, I think it's really easy to graph this. And it's also easy to write your interval notation. So let's take a look at this one, and at the end, we will do that interval notation. Now, this is your squeeze play, and I like to leave an and if it is able to be squeeze play, and not all ands are. They have to have that same thing to be able to do this, same situation with the variable. But since this one is already squeezed, it's this greater than 1/2 and this less than 5. You don't have to pull it apart to solve it. You can solve it in this form. So let's do this one in that form and you'll see how easy it can be. So basically you look at your variable and you say, I want to isolate him. And I've got 3 numbers here that I got to go. I've got a dividing by 4. I've got the subtracting 1. I've got a multiplying by 3. So the first thing is the entire numerator is being divided by 4. So we could clear the fraction by multiplying that denominator. So we're going to multiply by 4, but we're going to do the left, the center, and the right. Everybody's going to get multiplied by 4 because there's really, this is going to sound crazy, but there's 3 sides to this, kind of a left, the middle, and the right. So I'm going to multiply 4 times 1/2. When I multiply in here by 4, these will cancel, and 4 times 5 gives me 20. And look already how easy, or much more easy, this looks. I'm going to add 1, but again, to all 3 pieces, add 1 to the 2, add 1 here, and add 1 to the 20, and this is the way you show your step. I'm going to get 3 on the left hand, I'm going to get 3x in the middle, and I'm going to get 21 out here. And then the final step to get the x by itself would be divide everybody by 3, and when I do that, my final inequality, compound inequality, will be all numbers greater than 1 and less than 7. Now, I think this is really easy to graph because basically you just come to the 1 and you come to the 7, you put the appropriate points, filled in or not, and then you create the dumbbell with the points inside. It's also really easy to write your interval notation. Remember, you've got 1 on the left-hand side, 7 on the right, and since they're both without the equals, it's going to end up looking like a point, but that's your interval notation. So there's an example of an and done where I pulled it apart and we did it separate, and then I left it squeezed together. So here's one. Why don't you pause the video and see what you can do with this one. All right, so simpler than the one we just did. I'm not going to pull it apart. I'm just going to subtract 4 from everybody. When I do that, I'm going to have -6. I'm going to have an x, and I'm going to have a 4. Look, I'm already at my answer. Now I'm going to write my interval notation. Looks like a point when you don't have an equals there, doesn't it? Looks like, an x comma y, but it's the interval notation for this inequality. And then the graph, open circle at -4, open circle at 4, open circle at -6, open circle at 4, and then, all the numbers in between. And that is an example of a compound inequality that is an and. So let's go back to the other car on the conjunction junction train, and we're going to do an or. And again, I'm giving you that picture up here again of what we kind of expect the or to look like. So I'm going to just take them separately. I'm going to, solve this 2-step inequality like we've been doing. I'm going to subtract 3. I'm going to end up with now a 1-step. I'm going to divide both sides by 2. That is not the glitch. It's not going to flip the inequality. So I end up with x is less than -4. That's one arm of my or inequality. And up here, I'm going to add 2 and show that step. And I end up with all numbers greater than or equal to 5. Now be careful. Your answer here needs to include the word or. It's a compound inequality. That matters, okay? So now what's my interval notation? So I have 2 pieces here, and or cannot be squeezed together, right? It's all the numbers less than 4. It's all the numbers greater than or equal to 5. These are not overlapping. So we need 2 separate arms to our interval notation. So all the numbers less than -4, think of that graph kind of going off to the left. We're going to start at -infinity, and he always has a parenthesis, never a bracket. And we're going to go up, and it's going to be bounded on the top by -4 with a parenthesis. And then we're going to put the word or in there as well. And then this piece is bounded on the bottom by 5 inclusively, and it's going to go forever up to positive infinity, where it's not bounded. It has a parenthesis. So or inequalities cannot be squeezed into one. Just know that. They're 2 separate arms to the to the picture. So if we wanted to kind of graph this again, just to see it, remember we're going to graph this piece less than open hole to the left for, going less than for -4, closed in at 5 going to the right. And there is what we're kind of expecting. Since this is an OR inequality, the solution includes any point by either graph. I mean, that is your graph, and I have no idea why I did that twice. Anyway, here's one for you to try. How about if you pause the video and try this OR? Okay, let's see how you did. Really simple little inequalities. Over here, I'm going to divide both sides by my -3. Did you catch that that's the glitch? So it needed to flip and become less than. So this one was going to be C is less than -3. And on the other side, you're going to divide by -4. And did you do the same thing over there? I just wanted to remind you that when you multiply or divide by a negative, you've got to flip your inequality. So again, your interval notation is going to be 2 pieces, and your graph is going to be 2 pieces. And the only time an OR won't look like that is if it's that overlapping case that we saw sort of at the beginning that I called a weirdo. So there is our graph. So that's what an OR inequality is. So basically, compound inequalities are just doing what we did last section, but we're just putting 2 of them together. So, where is this used? We started kind of talking a little bit about going out to dinner and going to the football game, but here is a really kind of good example of where a lot of times there's tolerances. So we're going to do the acidity in a swimming pool, but even parts in an engine, making sure that they're within a certain size, or the inequalities are used a lot that way. So the acidity of the water in a swimming pool is considered normal if the average of 3 pH ratings is between 7.2 and 7.8 inclusive. That means it includes the 7.2 and the 7.8. If anybody has a swimming pool, you take kind of a little strip, you can check chlorine, you can check, in this case, acidity. You can put this little strip in and you match it to see how your pool's doing. So let's say you go out to your pool and you dip the stick in, and the first acidity reading says that you're at a 7.0, which realize is below. You're a little nervous, so you do what you have to do with chemicals and such, and then you do it again, and you get a 7.9, which is a little high, right? Now, you're going to do one more, and we want to know what could be the possible readings to be able to get this to be normal. And, it might not be a big deal if you're slightly off for your swimming pool, but if this was a public swimming pool, there's, regulations that they have to adhere to. So the first thing is our variable. What possible value? So what is the, third reading to make this normal, right? So we're looking for that third pH reading. So we're going to write an inequality, and let's think about that we're doing an average. When you do an average, you're going to add up everything and divide by how many, right? So we're going to add up, over here, what we've already done, plus that missing one, and divide by how many. See if you can write that inequality, remembering what has to happen here. Give it a go. Pause the video and see if you can do it yourself. All right, let's see how you did. So basically, we're going to take the 7.2 is one endpoint. That's the bottom. That has to be less than or equal to the average of the 3. So you have to add the 3, divide by 3, and that number had better be greater than or equal to 7.2 and less than or equal to 7.8. So this is your equation. And now it's a squeeze play that we're going to solve. So can you solve this squeeze play? See if you can do it right now. Pause the video and give it a go. Okay, I'm going to advance this because I have it all typed out over here. All right, so here is the inequality that we're solving. I would have started by multiplying all 3 spots by 3. Right, so we're going to multiply everybody by 3. That's how I'm going to show it. And already things are getting easier. And I also did the like terms. I added these 2, which is fine. And now we're down to kind of a one step. I'm going to subtract 4.9 from all 3 spots. And here is the answer to the question. So when you go and you dip the stick into the pool, your reading has to be greater than or equal to 6.7 or and less than or equal to 8.5 for it to be legal at that point. Okay. And that solution would look like this. So if it comes out to be an 8, if it comes out to be an 8.4, if it comes out to be a 6.8, you're good. If it comes out to be a 6.5, you're not. So today we learned about compound inequalities. We started off with a little bit of a song, remembering and or, conjunction, junction. And those are the two that we are looking at. And you're going to see, you're going to kind of expect it to come out looking like this, like the dumbbell. And the or, remember, is going to be the two arms pointing in opposite directions. Remember when you're solving these that the and can be squeezed, but an or cannot. Also, just a crazy one, but make sure when you're doing this, if you have the glitch and things kind of flip, make sure that you're graphing on the number line correctly. Crazily enough, I've had people kind of end up with a negative over here and a positive over there, and they make the number line go in the wrong direction. Please don't do that. So you might see that happen in one of the practice problems. But anyway, just kind of remember that the number line has to go, least to greatest kind of thing. So again, and or, compound inequalities, not really tough. Time to practice. And guys, I really do hope you have a great day.